Welcome to learning module number 2, atomic structure and bonding. To truly understand the material's properties, we need to understand how atoms bond with each other, because the type of bonds between atoms define the overall properties of the material. All right, well, let's start with a very simple question, which is, what is atom? Okay, so hopefully the majority of this information is not new for you, and I'm pretty certain that you've been exposed to this material at some point. I will be bringing quite a bit of information that you are familiar with, but I will be telling you all that information from a perspective of the material and the material properties. Now, atom is a basic unit of an element, right? Basically, this is the smallest part of an element, right? The tiniest hydrogen is going to be the hydrogen atom, right? What we know is that the size or the diameter is usually 0.1 nanometers, right? And then we also know that the atom is neutrally charged. At the core, right, at the center of the atom, we have a nucleus, right, which is very, very small. And that nucleus accounts for almost all mass of the atom. Now, we also know that it is positively charged. Why? Because it hosts protons and neutrons. Now, the mass of either proton and neutron is very, very similar. You guys can see the numbers right here, but the major difference is the charge. Protons are positively charged, whereas neutrons are neutrally charged, meaning that the nucleus is positively charged due to the protons in it. Okay. Now, we also know that the area surrounded by the nucleus is occupied by electrons, and we usually say an electron cloud, right? Now, the electrons are very, very light. Much lighter than either protons or neutrons, and they are negatively charged. The electron cloud accounts for all volume, meaning that the nucleus is extremely small compared to the entire volume of the atom. Now, scientists discovered it long before we invented very powerful electron microscopes or atomic force microscopes, right? Now, question is, how did they come up with this theory, right? Is there an experiment that demonstrates the structure of atom? Meaning that, is there an experiment that does tell us that the majority of the atom is just a free space, right? Free space available for electrons to exist. And now in the center of it, there is a tiny, tiny, very small nucleus. There is an experiment like that, and it has been conducted by the Rutherford, and this is why we know it as a Rutherford experiment. Um, as usual, every genius idea is very, very simple. So what he's done is that he took a radiation source, specifically radium, and then radium basically emits alpha particles. Okay, it allows you to emit these alpha particles, and something that you need to remember about the alpha particles is that they are positively charged, right? So you have a beam of positively charged particles. And for now, I want you to skip whatever you guys see in the middle. I want you to just understand that he used a fluorescent screen. And then when the beam was passing through empty space, he was able to see the beam right here. Okay? So you could see that all of the fluorescent screen allows you to visualize those particles, right? So, and you could see the beam at the other end of the fluorescent screen. What he did next is that he took a very, very thin gold foil. Okay, and the idea is that now he placed it in front of the beam and he wanted to see what's going to happen to the beam. Now, what was happening is that the majority of alpha particles, they passed through the foil right here. Okay, they passed through the foil as there was no foil in front of them. That allows us to conclude that most of the atoms must be made up of an empty space, right? Then a few of the alpha particles were either slightly deflected or completely bounced back, right? So that tells us, and keep in mind is that the alpha particle is positively charged. That means that the nucleus at the center of the atom houses positively charged particles. And keep in mind is that like charges tend to repel, right? And this is why we see the deflection or the alpha particle bouncing back. But since we did know that the atoms are neutral, right? And if you have something in the nucleus that is positively charged, right, that means that the numbers of protons must equal the number of electrons in the atom to make sure to comply with the fact that the atoms are neutral. If you'd like to see the visualization of this experiment, please follow this link at the bottom of this slide. Okay. Now, what do we need to know about all of the elements? Perhaps before I go there, I'll show you the periodic table of elements and what it looks like, right? And you guys know that there are certain numbers. We know that each element has a specific number next to it. All of the elements are ordered in a very specific order. There is a reasoning behind it. We can't just swap them. And actually, from the position of the element in the periodic table, you can predict quite a few properties. And by the end of this lecture, you'll be able to do that. Now, but you also know that there is another number that is at the bottom of the element that also means something. So why don't we look at those numbers? So for each element, you usually know the atomic number, mass number, and atomic mass. Now, atomic number, which is Z, letter Z, is unique for each element, and usually it defines the number of protons, not usually, it defines the number of protons in nucleus. And this is why, let's look at the example. So once again, the Z value, the atomic number, is unique for every single element, and it defines the number of protons in the nucleus. Hydrogen, the atomic number is 1. Carbon, the atomic number is 6. Let's look up the numbers and find those examples, right? Here's your hydrogen, and here's your number 1. This is the atomic number for hydrogen. And here's your carbon that has the atomic number of 6. And each number is always unique for every single element, right? Now, there's also a mass number, right in here, which is the sum of protons and neutrons in nucleus. Okay, so for example, for hydrogen, the mass number is 1 because hydrogen only has 1 proton, right? And then for carbon, it is 12, okay? However, if I am to look back into the periodic table, you won't see the numbers that I just mentioned, 1 and 12, right? And specifically, I'm still looking at your hydrogen, and I'm looking at your carbon right here, right? Instead, you see the numbers such as 1.008 for hydrogen, and you see 12.01 for carbon. This is not a mass number. This is an atomic mass, okay? Or sometimes we also say average atomic mass. Now, it is basically the mass of an atom, and it is expressed in atomic mass units. And one atomic mass unit is the same as 1/12 of carbon atom. But you're probably wondering, okay, but where does that number come from? Because for carbon, right, the mass number is 12, meaning that there are 6 protons and 6 neutrons. My apologies. 6 protons and 6 neutrons. That brings up the question, so where does that 0.01 come from, right? Well, that comes from isotopes, okay? So Pretty much every element has some variations, and those variations of element with same atomic number, which is your number Z, right, which is the same number of protons, but different mass number. So the mass number is A, okay? So how can you have the same number of protons but a different mass number? Well, the difference comes from the number of neutrons. And let's consider isotopes of hydrogen, okay? So we know that there are three, and specifically there's the protium, deuterium, and tritium. I may be pronouncing it wrong. But the only difference is that protium will have one proton, right? Um, Now, deuterium will have one proton and one neutron, okay? And then tritium will have one proton and two neutrons, okay? And so this is why our mass number is going to be 1, 2, and then 3, right? But each have exact same number of protons, and this is why the number Z, the atomic number, is identical for all. Now, if you are to estimate the atomic mass, right? Atomic mass has to be the average, right? If all those three exist, you have to take into consideration the mass of each because it will differ. And then you also have to take into consideration the occurrence, right? In terms of the weight percent total existence on the Earth. And that's how you come up with this average atomic mass, which is usually slightly different from the mass number, okay? Because it does take into consideration the isotopes. Perhaps we shall consider an example. And since later on we will be dealing a lot with iron, right, and corrosion, it makes sense for us to consider iron for this example, okay? So iron has four isotopes, right? Uh, those are iron 56, right? And this is actually most abundant. Now, iron 54, right? And this is molecular weight. And this is basically the weight percent of that specific iron on Earth, right? And then you guys, of course, have another two, okay? So iron 57 and iron 58 are a lot more rare, okay? So now, taking this as an example, we would like to be able to answer the following questions. First, we need to find the relative atomic mass of iron. And then we're going to compare our answer with the value in the periodic table. Okay, I'm sure some of you want to know the answer right away because we see these numbers, right? We see this almost 56, 54, 57, 58. What is the number in the periodic table? Well, why don't we find it uh, right away? Okay, here's our iron, right? And the atomic mass is 55.85, right? We're going to put it in here. 0.85, and the units is going to be AMU, right? Atomic mass units. Then we would like to find out how many atoms are in 1 gram of iron, and then what is the mass of one atom in grams. Okay, let's go one by one, okay? So starting with question number 1, we need to find the relative atomic mass of iron, okay? So how would we find it? As I said earlier, we just need to take into consideration all of the existing isotopes, right? And of course, their weight percent, right? So how would I do that? Well, I'll start with each and I'll go in the following order. 55.934, right? This is the iron 56 times 91.754 plus 53.939 times 5.845 plus 56.935 times 2.1119 plus 57 times 0.933 times 0.282, right? And then, of course, to find the correct answer, I would have to divide it by 100. So if I am to take this into consideration, I've done my math earlier. Roughly, it is, I'm rounding it up to one digit. It's going to be 55.8 atomic mass units, right? And just to compare what was in the periodic table is 55.85, which is actually the exact number, right? And that's the number we should go with. Now, this is the average atomic mass. For us to find the relative atomic mass, it is actually going to be the exact same number, but the units will be gram per mole. So the relative atomic mass is going to be 55.8 grams per mole, right? That is the correct answer. Based on the isotopes that we were provided. However, for any further questions, I recommend we're going to go with a more precise answer that is given by the periodic table, which is going to be 55.85, right? Next question. How many atoms are in 1 gram of iron? Okay, so earlier we just found out that the relative atomic mass of iron was 55.85. Again, I'm going with the value from the periodic table, gram per mole, right? Now I need to identify how many atoms are in 1 gram. Okay, well, if this is gram per mole, I know that I have, and I'm going to go with the Avogadro's number, right? There's going to be 6.02 times 10 to the power of 23 atoms in 1 mole, right? And I know that this is unique for every single element. Now, if I am to consider this 0.02 times 10 to the power 23 atoms of iron atoms, right? I know that the weight of it, the mass, is going to be 55.85 grams. So how would I find the number of atoms in 1 gram? Well, relatively easy. I just need to take this Avogadro's number, right? And I need, if this is going to be atoms, and I need to divide it by the grams, right? And this would give me 1.078. Perhaps let me correct this. 1.078 times 10 to the power 22 atoms, right, per gram. And this is how we answer the questions. That's how many atoms you would have in a 1 gram. And perhaps I should specify of iron, right? Because depending on the element, that number in the denominator will actually change, right? Because some atoms are heavier, some elements are lighter. And the last question would be, what is the mass of 1 iron atom in grams? Okay, well, we do know that going back to what we found before is that we know that 55.85 grams, that's the mass of the number of atoms equivalent to the Avogadro's number. So if I take that mass and if I divide by the Avogadro's number, I will end up with the mass, which is going to be extremely small, of a single iron atom, right? Gram iron atom, right? Just to familiarize you a little bit with the periodic table, the numbers you see there, the concept of isotopes, and mostly to just kind of like make you a little bit familiar with the units, right? Now, let's do a few more exercises that are a bit more interesting, okay? So we have 100 grams of alloy of nickel and copper, and we know that the 75 weight percent is copper and the 25% of nickel right away. Okay, so if I have 100 gram, right, if my basis is 100 gram, then I know that 75 grams is going to be my copper and then 25 grams is going to be my nickel. Now I can also get the atomic weight for each, right? This is the top one is for copper, the bottom one is for nickel. And again, this is atomic weight, but for me, I'd rather use a relative atomic mass. I'm going to use units of gram per mole instead of atomic mass units, right? Just to simplify the thing. Now, what is, to simplify the question, what is the question here? What are percentage of copper and nickel atoms in this alloy? Okay, so basically, to solve this entire problem, right, because we need to find out the percentage of atoms, right? Even though you know the mass of copper and nickel, right? We need to convert it to the atoms, and once we do that, we also need to convert it to the percentage. Well, this is actually a relatively simple problem because all we need to do is we need to go to moles, right? Because there's exact same number of of atoms in a mole of either copper or nickel, right? Even though the weight of it changes, the number of atoms in a one mole is always the same, right? So how would I do that? Well, and I'm gonna go the following way. Perhaps I'm gonna find the moles first for copper, right? And how would I do that? Well, I'm gonna take my weight and I'm gonna divide it by the relative atomic mass, right? 63.55 gram per mole. This would give me 1.18 mole. Now I'm going to do the identical exercise for my nickel, right? Which is going to be 25 grams divided by 58.69 gram per mole. Now, perhaps before I proceed any further, 0.43 mole, right? This is how I find the number of moles for each of the elements. Before I proceed any further, I'd like to remind you that this atomic mass, the 63.55, and the atomic mass of 58.69 is obviously taken from our periodic table, right? So all of these numbers can be found in here. And let me point it out for you here, right? So I'm looking at the nickel, right? This is the number right in here. And next to it, we have the copper, right? And right here. Okay, so just so you know, in case if the homework or the quiz or the exam, in case they do not specify the atomic mass for you, just keep in mind that you can easily pull it out from the periodic table. Periodic table will always be supplied with every question. Okay, so now that we know the moles, we just need to find the percentage of atoms, right? Well, this is going to be very easy. How would I do it for copper? Well, I'm going to take my number of moles and I'm going to divide it by the total. And the total is going to be 118 plus 0.43. Also moles, right? And that would give me 73%. I'm rounding it up to just integers, okay? And that means that I have 73% of copper atoms. Right away, I know that I will have 27%, which is the remaining of nickel atoms. But perhaps we can also do the math just in case to double check, right? Um, I'm pretty sure it's going to give you the 27%. Um, that is pretty much it, right? And then some of you may be thinking like, well, hold on, how do you go from mole to atoms, right? I mean, you could still multiply top and bottom with an Avogadro's number, right? Because that's how you link, that's how you go from moles to the atoms, but it is completely unnecessary because the Avogadro's number will cancel out, right? Because you will have to multiply both the numerator and the denominator. So I'm kind of like taking a shortcut, and the moment I convert it to moles, I can right away start working with the answer because the answer will not change. Let's do one more exercise, which is very similar to the one that we solved above. So we have an intermetallic compound and it has the chemical formula of this. I love it. It's a nickel X aluminum Y. So we don't really know what the X and Y, and obviously this is where we want to find out, but we do know that X and Y are simple integers. Now we know that this compound consists of 42 weight percent of nickel and then 50, roughly, I'm just rounding it up, 58 weight percent of aluminum. Okay. Now, what is the simplest formula of this nickel aluminide? Basically, we need to identify X and Y. Okay. So, well, if I am to consider the basis of 100 grams, then I know that I have roughly 58 grams of aluminum and I have 42 grams of nickel, right? And they have this atomic weight. Again, instead of using the atomic mass units, I'm just going to right away use gram per mole, right? The relative atomic mass, the number is the same. It does not change. It's just the number of units. And so all I have to do now is to basically find the number of moles, right? Because this is the only way for me to actually convert to use the chemical formula, right? Because we always operate with moles. So how would I do that? I'm gonna go with the following way. Okay, so I'll start with aluminum. Um, And I know that I have 57.96 grams, right? And question is how many moles of aluminum I have. Well, given that the relative mass is 26.98 grams per mole, that would give me 2.15 mole of aluminum, right? This is what, well, perhaps I shouldn't say of aluminum since I already wrote it before. Now, same way, I'm gonna estimate the number of moles for nickel, given that I have 42.04 grams divided by the molecular weight, right? 69 gram per mole. And that would give me 0.72 mole, right? So now I know the number of moles, okay? Next question is to find the mole fraction of each, right? Because once I know the mole fraction, I can take those numbers and convert them directly into the chemical formula, okay? So pretty much same way. So what is going to be the fraction, the mole fraction of aluminum? Well, it's going to be 215 divided by 215 plus 0.72. And this would give me 0.75. Now, without even doing the math, I'm just going to use a shortcut because I know that the total mole fraction is 1. So that means that the remaining 0.25 is going to be my mole fraction of nickel. Okay. So if I am to basically write down nickel 0.25 and aluminum 0.75, I could submit this answer, right? However, if I am to read back the question, it says, what is the simplest formula? That means I still need to do a little bit of simplification, meaning that I can divide each by 0.25 and I will end up with nickel aluminum 3, right? And this is the nickel aluminide that I should be able to find. Again, this is more of a refresher and throwing at you periodic table. I want you to get comfortable with it. I want you to see the numbers there and to understand which number represents the number of protons, which number represents the atomic weight, right? What are the units and how can I go in between units to be able to solve problems like that, okay? Now, well, now that we know what atom is characterized, right? We know what it consists of. We know what it what we can use to characterize the atom. The next thing, before we can bond atoms together, right, we need to understand the electronic structure of atoms. And this is probably one of the most important concepts for today's lecture. And I'll try to simplify it as much as possible. I'm not going to bring any quantum physics or chemistry into this class. I'll try to minimize those as much as possible or perhaps shorten, but I will deliver you the most important concepts that will explain you what happens when you have an atom and you have a bunch of electrons in that atom, okay? So perhaps we have to first, before we understand the electronic structure of atoms, and that means that, okay, we know that in the center there's a nucleus, and we know that the rest is the empty space. But that empty space is called the electron cloud, meaning that that space is occupied by electrons. But if it is occupied by electrons, right, how is it occupied? Is it do you have an electron that just rotates around a fixed orbital, or can it exist everywhere? And if it exists everywhere, what is the probability of finding it in a very specific spot? And where does it happen to occur longer, right? And basically, where's the highest probability and things like that. Before we get into that, there were two major discoveries that we would need to understand. Right, first is that Max Planck, the German scientist, he made a very major discovery, and specifically, he said that the atoms and molecules emit energy only in certain discrete quantities, which is called quanta, right? And that energy is usually described as h nu, where h is your Planck's constant. You guys can see this number right here, which is 6.63 times 10 to the negative 34 joules time second. Now, nu is the frequency, okay? And the reason we are using frequency there, because earlier James Maxwell, he said that the visible light is the form of electromagnetic radiation, okay? And so basically, the energy that is emitted by the atoms and molecules, not only it always exists in discrete quantities, it is also a form of electromagnetic radiation. And if it is an electromagnetic radiation, that means it's basically as a wave. It can be described with the frequency and the wavelength, the frequency, wavelength, and the speed, right? And so this is how you can go from the frequency nu to the wavelength, right? Knowing that the frequency is the same as the speed of light, which hopefully people remember 3 times 10 to the power 8 meters per second divided by the wavelength. And the wavelength is usually measured in nanometers, okay? Most commonly. Now, before Max Planck said it, right? And the important thing is that energy is always released in integer multiples of h nu, meaning that you will always have the energy that will have some kind of integer number here, and then you have this h nu, what is known as quanta, okay? And the n number is always an integer. It's never in between. It can be 2.5. It can be either 2 or 3, right? Or any other integer number, but never in between. Um, um, okay. So the question was, if that is the case, if the energy is not a continuous wave, but it's actually these portions, right? These specific integer portions, can you visualize it, right? Because once again, you have an atom that is capable of emitting these discrete quantas. Can I somehow capture it and can I see it? Well, if that is the case, right? Bohr comes with his theory, taking everything into consideration, that all the energy is released in distinct quantas. He basically says, okay, so the electron rotates at definite energy levels. And for simplicity, we're going to represent it as these energy levels, right? And they are described with principal numbers. So right now I'm showing you 3 energy levels, right? Labeled as 1, 2, and 3. Now, what he says then is that for the electron to move to the higher energy level, and specifically right now, with this arrow, I'm showing you transition from the level 2 to the level 3. It needs to absorb an energy, and we call it a photon. Now, the opposite transition, right? So the energy is absorbed to move to a higher level. The opposite transition, I'm going now, the electron drops back from level 3 to level 2, then the energy is emitted during the lower transition. And he went and just giving you a spoiler right away. And it worked beautifully for hydrogen. We are about to see the evidence for it. And he even developed a formula that allows you to actually estimate the energy of each level, right? And then this number, we usually measure it in electron volt. And this number right here, it's a constant. And you can refer to our textbook to actually see what is inside the constant, but there is the electron charge, there's the electron mass, probably something, mostly electron mass charge, and there's the Planck constant inside of it. But that's how you get the 13.6. Now, and it is divided by the principal quantum number, which is 1, 2, 3, and so on and so forth. Those are actually the energy levels that you guys see as orbits, right? Now, the one thing I will say, I see it right away, is that it is missing the minus sign. You're supposed to have a minus sign in this formula, okay? It is actually negative 13.6 divided by n squared. Now, is it possible to prove it for this entire theory, right? That for electron to move in the atom the way it does, right? Basically, hopping from one level to the other. If it goes to a higher energy level, then it needs to absorb the energy. If it hops back to the lower energy, it needs to emit the energy. And especially if you emit the energy, you should be able to see that, right? So it turns out that his theory worked beautifully. And before I show you how he was able to demonstrate that, right, we will solve one problem. We kind of like, we'll get very close to his research and to see how simple his findings were. But again, simple yet genius, right? Let's say if we're looking at an electron that undergoes transition from level 3 to level 2, okay? So it's dropping down, okay? And if it does drop down, based on the Bohr's theory, it must release a certain energy, right? And that means that we should be able to detect that energy. Now, and if we ought to do the math, the energy of photon emitted is going to be this, right? Well, minus sign is forgotten here, so I have to put it in here. And this minus actually signifies the fact that the energy is released, right? It is emitted. And it is 1.89 electron volt, and this is what we can measure. But the question is, what is the wavelength of such photon? And the reason I'm asking why you want to know the wavelength, because we are about to find out that the wavelength of that photon is going to be somewhere in the visible light, okay? And if you guys remember, this is the spectrum of all electromagnetic, this is the entire electromagnetic radiation, right? And we have the gamma rays, the X-rays, the UV, the visible light, the infrared light, and the radio waves, right? And we use all of those depending on the purpose. But right in here, this tiny, tiny portion includes the visible light. And if I am to take this visible light and actually squeeze it into one beam, the color is going to be white, right? But once I stretch it, the color is, I can see all these beautiful colors, and hopefully people recognize that's the rainbow, right? Because the sun arrives to us as the white beam, right? That's why everything's so bright and it's white outside. But whenever the rainbow occurs, you probably guys noticed that it always happens right after the rain is almost over, right? It's because you have the drops of water that are still hanging in the atmosphere, and then when when the sun hits this water drop, it acts as a prism. It dissipates the light, and that's how you now see all of the colors, right? Because why you see that? Well, because some of the colors are fast, right? And what I mean by that is that their wavelength is very short. And whenever you have a short wavelength, you have a higher energy. And you guys can see it from here, right? I will remind you. So if this is my energy and the connection is like this, okay? So keep in mind is that H and C are constant and the wavelength is something that you can change. The smaller this value, right? The smaller this value, the higher the energy. And this is why the UV light is a lot more dangerous, a lot more powerful than the red or even further infrared, right? So the energy is actually increasing this way, right? The shorter the wavelength, the shorter the wavelength and higher frequency, right? Because you'll have to see something like this. This would be the UV light. The red light would be something like this, lazy, right? And kind of like very long wavelength and very small frequency and low energy. Okay, but I'll tell you right away, that photon that we are about to estimate, the 1.9 electron volt, is somewhere in that visible light. But if that's the case, you should be able to see that color, right? So why don't we find out what that number is? Okay, 1.8 electron volt. Now, for us to do the conversion to nanometers, we will be using the following equation, right? I will duplicate it here again. It's hc divided by wavelength. From here, I know that the wavelength is the same as hc divided by the energy, right? The energy here is given, which is 1.89 electron volt. Now let's just put everything in here. We'll start with the Planck constant. The Planck constant is 6.63 times 10 to the negative 34. The units are joules times second. Now, in case I shall point out once again where I showed it early on, this is the number right here. This is the Planck constant, right? Now, going back in here, I'm multiplying it by the speed of light, which is 3 times 10 to the power of 8 meters per second. I'm going to switch the color right. Actually, I will do the units right after. I'll take a time to go over the units too. And then I'm going to divide it by the energy. And the energy is 1.89 electron volt. And something to keep in mind is that a 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joule, right? This is the conversion, and I will have to use it. Why? Well, because my Planck's constant uses joule, right? This is why I'm gonna multiply it by 1.610 to the power of negative 19 joule. Okay, now let me see the units. I have to be left with some kind of meters, right? But I will convert it to nanometers right away. So joule divided by joule, second divided by second, and it leaves me with meters. Units work out. If I am to do the math, it's going to be 6.577 times 10 to the power of negative 7 meters. And I'm going to convert it, as I said, that typically the wavelength is usually measured in nanometers, right? And if we talk about the visible light, so if I am to somewhat um, round it up, I'm just going to put it as 658 nanometers, right? So this is going to be the wavelength of such photon, okay? Now, let's go back to that bar with the visible light, right? Because I wonder if we can identify the color. Okay, so if I am to look at here, I am at 658. I'm somewhere in here, right? So like somewhere in here, we have like this 658 nanometers. So now let's go back to the question. I want you to first analyze the color. It's going to be some kind of a reddish tone, right? So if I am to go back to this question, when it says that when you have an electron that transitions from level 3 to level 2, it emits this energy of 1.9 electron volt. And we just found out that it is, in terms of the wavelength of such photon, right, you should be able to see the red color, okay? So that means this specific transition, the one that is depicted right here, this transition, shall be seen as the red light, okay? And the beauty of it is that for hydrogen, that is exactly what you see. And specifically, that transition from level 3 to level 2, which is going to be this transition right here, right, to level 2, it belongs to Balmer series. And you can actually visualize it with what you see, and you can estimate all other transitions and find their names too and identify those transitions as well. So you can imagine the significance of all these discoveries, and specifically the discovery, uh, the Bohr's theory, right? Because everything he said was just confirmed using the hydrogen atom, right? And he wouldn't be able to come up with this equation or even come up with his explanation where you have the electron that rotates at definite energy levels and how you can estimate those energy levels. He wouldn't be able to arrive to this conclusion if he didn't rely on the findings of James Maxwell, right, about the electromagnetic radiation, and the Max Planck, where he said that the atoms and molecules, they emit energy in certain discrete quantities, okay? Now, everything would be wonderful. However, the problem is that the Bohr's theory only worked for hydrogen. Uh, and the unique thing about hydrogen, hydrogen is the only element that has only one electron, right? So every other element, helium, and from that element going any further, you have two or more electrons. And that is the problem. The Bohr's theory fails to explain other elements. Okay. This brings us to Heisenberg. And I'll keep it very short. What he does is that he comes with the uncertainty principle. And why this uncertainty principle is important is because Bohr's model fails to explain multi-electron atoms, right? And multi-electrons atom, as I just explained, it's every element except hydrogen, right? So what he does is that Heisenberg, first, he rejects the Bohr's concept of orbit of fixed radius for an electron. It's pretty ballsy, but that was a very, very important discovery. He basically says the electron doesn't rotate around an orbit with a fixed radius. It's not like that. There is more to that. And he explains it. I'm not going to dive deep into there, but he introduces the uncertainty principle that looks like this. And the idea is that it is impossible to simultaneously determine the exact position and the exact momentum of body, right? And he worked with momentum, right? But we mean like the velocity. And this is your uncertainty in the position and uncertainty in speed. And what we can do is that we can only provide the probability of finding an electron with given energy within a given space. And this is why we always talk about the electron density or the electron cloud. I'll show you what the electron density usually looks like. Let's look at this figure number A. You kind of see this sphere, and you probably will notice that there is a gradient in color. It's darker, and this dot right here, it's your nucleus, okay? So you can probably see that it's kind of darker toward the center and it dissipates toward the edges of the atom. Well, why? Well, because the probability of finding the electron near nucleus is higher than at the edges. Now you can even define the boundary surface. This boundary that you see right here determines the space in which the probability of finding the electron is 90%. I'm not going to go further into the radial probability, but it does explain you the concept of this uncertainty principle, right? So that basically means that the electrons, they can exist anywhere in that space. And what you can do is that you can define the probability of the electron existing or finding the electron at a specific energy level. Now, this theory actually, and specifically rejecting the concept of a fixed orbit, has defined the fundamental explanation of the electronic structure for multi-electron atoms. And I'm sure the sketch that you guys see on the right is something that you've seen before, right? But just to explain something, to point out something very quick. If you've seen before that we had fixed radius, we had level 1, level 2, level 3, but now if you look at it, you'll see, okay, well, I have this level 3s, but then there is another level 3p, and then there's another level 3d, right? And you can see, so what happens is that there is a splitting of energy, right? Now, when and why it happens, we call it energy splitting. When more than one electron exists, and again, every element except hydrogen, why that happens, why the energy splits? Well, the electrostatic attraction effects between electrons and nucleus, as well as repulsion forces between electrons, lead to more complex energies. And I want you to, for a second, to envision it, right? So you have a nucleus which is positively charged, and then you have a bunch of electrons, right? This is in multi-electron atoms, or even two. You need at least two for the energy splitting to occur. Now, nucleus is positively charged, and of course, there's going to be electrostatic attraction between the electrons and the nucleus, right? And that's how the atom is kind of like held together. But at the same time, if you have more than one electron, that means that there will be also repulsive forces between negatively charged electrons. Why? Because they have the same charge, they tend to repel, right? Now, because of these two coexisting, right, the electrostatic attraction and electrostatic repulsion, we observe these energy splitting into more complex energies. We don't see just these quantum numbers or energy level 1, 2, 3 anymore. Now we see splitting of energy. Each energy level splits into more available states, okay? Now, what else we need to know, and this is really, really important phenomenon, and this is called a nucleus charge effect. Specifically, what it means is that the higher the charge of the nucleus, and one way to think about it, the more protons you add to your nucleus, the higher the attraction force of an electron, the force on the electron, and the lower the energy of the electron, or perhaps we should say the more negative the energy of this electron, right? So once again, the stronger or the higher the charge of the nucleus, right? And you guys can imagine in the periodic table that would be going from left to right, right? Because if once I go in the direction, I add more and more my protons. So what happens is that the force which pulls electrons toward the nucleus is significantly stronger, right? And I'll give you an example. Let's consider something that is very, very similar. I'm going to look at the hydrogen, right? And you guys know that there is only one proton in the center and there's one electron, okay? And this is the energy of that electron, which is negative 1300. So how shall you think about it? It says negative, and I want you guys to understand. For many applications, you have to steal an electron away, and it comes at a price. That specific number is the price or the cost you have to pay to steal an electron, okay? And this is why it's negative, because you have to pay it, okay? So that means that for my hydrogen, which only has protein in the center, protein, someone is hungry, proton in the center and has one electron, right? Then this is the energy of that electron, negative 1300. Now I want you to look at helium plus. And just so you guys understand, helium is the second element. So it still has it has two protons, right? And it has two electrons now. Okay, it has two electrons now. But because it has helium plus, that means that one of the electrons was stolen. And now I'm looking at the system that is somewhat very similar to my hydrogen, right? But what happens is that because the charge on my helium, right, the charge on the nucleus is larger than what you have on the hydrogen, even each of those have only one electron, right? But the electron on the helium plus has a significantly lower energy, right? It's more negative, right? And we call it lower energy because it means that if I am to take those two, right, and each has only one electron, right, they kind of very similar. And if I am to attempt to steal an electron away, it would cost a lot more energy to do so from helium plus because of a nucleus charge effect. Now, the next effect that you should be very familiar with is the shielding effect. The electrons, right? Again, it's a multi-electron atom, shield each other from the full force of the nucleus. Specifically, the inner electrons shield the outer electrons. So what I mean by that is when you have a nucleus and then you have a bunch of inner electrons and then you have this outer electrons, which we also call valence electrons, right? The inner electrons, they shield the outer electrons from the full force of nucleus. And it kind of makes sense, right? Because keep in mind that all the electrons are kind of negatively charged. There's always this repulsion, right? And what that means? Well, let's look at the helium plus, right? Uh, let's look at the helium plus, right? So that means that there's only one electron rotating, right? And then I shouldn't have said rotating, right? But you guys kind of get the concept. And you want to look at helium where you have two electrons, okay? So you guys will notice that the energy of this electron is significantly lower, right? When compared to when you have two electrons. Because once again, the electrons, right, in multi-electron atoms, they shield each other from the full force of the nucleus. And especially, and this is why whenever we need to remove an electron from the element, we attempt taking the ones that are in the outer shell. Why? Because they are easier to steal. It's really hard to knock out an electron. It's possible, and you will guys see some applications of us doing that later in the course. It is possible, it is doable, but it requires a lot more energy to knock out the electron that is the inner electron close to the nucleus versus the one that is outside. Okay, so taking this into consideration, those two, right? Now that you understand the concept of energy splitting, right, and that kind of explains you that there is no fixed orbit. Now that you are familiar with two major concepts, and this is the nucleus charge effect and the shielding effect. Those two, in a sense, they intertwine. You will see how they intertwine because sometimes I will ask you to explain something to me, and you will think, well, it's kind of nucleus charge effect, but it's also a shielding effect. So you guys will see that these two they don't really exist on their own. But now knowing those two, you can explain a lot of periodic trends. And I know that at some point, maybe when you've been taking chemistry, we often had to memorize it, what happens with the size, what happens with the ionization energy, what is ionization energy. Well, hopefully today it will make sense because I will constantly be explaining it. When explaining it, I will go back to the charge effect, nucleus charge effect, and the shielding effect. Okay, so periodic table, as I said, all of the elements, they have a designated space. You can't swap them. They are in a specific space. And there is a reason they are in a specific space. Because looking at the periodic table, there's a lot of information that you can obviously extract, like let's say the number of protons, and then you can see the atomic mass, as we saw earlier in this lecture. But most importantly, often you don't have to know the information about a single element. Often you have to compare those two because often as a chemist, as a material specialist, as an engineer, you have to bond something together or you have certain elements to react with each other and you want to predict which one is going to steal electrons away, which one will donate electrons, and you can pick up all of that information from the periodic table. Or sometimes you look at two elements and you want to understand, well, which one is smaller, which one is larger. This will also be very important in our course. You can pick up all of those trends just by looking at the periodic table and finding the position of the elements in it. Okay, so let's start with each of the trends. First one is atomic size. It is very, very simple. So guys, well, first I'm gonna say what the size is, right? We usually don't take the element alone and measure the diameter. That's not how you should do it. You usually take two elements and you take half the distance between their nucleus. That's how you do it, okay? But that's not really important. We understand what the size is, right? But what happens with the size and how the size is related to the position? Well, as the principal quantum number increases, okay, and I want you to think of the following. The principal number, which is 1, 2, 3, 4, 5, and so on and so forth, that means you're moving top to bottom, okay? You're moving top to bottom. And what happens is that you have to host more and more electrons, okay? And that means that the electrons, they occupy farther positions from the nucleus. And as you have to host all of those electrons, the size increases. Okay, so going top to bottom, the size increases. Once again, why? Well, because you have more and more electrons, right? You're kind of like packing more and more, and you have to, the electrons are now further away from the nucleus and they obviously need the space, and that's how the size increases. Now, but as the charge of the nucleus increases, and this is, guys, really important, now I'm adding more protons and I'm moving left to right. So what it means is that I am moving from this to here. And right away you can see that these guys look very, very small, right? They look a lot smaller than whatever the guys on the right in every row, they look smaller than the guys on the left, right? Why? You guys can explain it already now, okay? If once I move from left to right, and I'm going to show it here, from left to right, if I move in this direction, I'm adding more protons. Protons are hosted in the nucleus, right? And protons is what increases the charge, the positive charge on the nucleus. And based on the nucleus charge effect, the larger the charge on the nucleus, the stronger it pulls the electrons toward it, right? And that means that the size shrinks, right? The atom, the electrons are attracted stronger to the nucleus and the atom shrinks. One way to think about it, right, because it's a positive negative interaction, right? Positively charged nucleus, negatively charged electrons. The more charge, it's like you are ramping up the charge on your nucleus. And because it's like a magnetic, right, plus minus interaction, or perhaps I should say Coulomb electrostatic interaction, right? The nucleus, because it gets so powerful, it pulls your electrons closer, and that means that the size shrinks. Okay? So once again, if I go from top to bottom, I'm hosting more and more electrons, and of course I need a space. My Airbnb has to be bigger and bigger to host all of those electrons, right? Electrons occupy further and further away, and that's why the size increases, okay, top to bottom. Well, if I go left to right, that means I'm hosting more and more protons, but the concept here is very different. The protons increase the charge of the nucleus. Now your nucleus, it's like you're ramping it up, and that means it's going to pull the electrons even stronger toward the nucleus, right, toward itself, and that means that your atoms, they shrink in size. Now, if I am to eliminate all this, change a different color, and if I am to describe the trend in atomic size, right? And I kind of like want to describe it as one trend. That means that the size increases in this direction, right? Okay, or in general, for some of you, we can kind of like point out it like this, okay? And you guys can see it. This is exactly what you see with each of the elements. In your textbook, if you do not own it, I'll make sure that I post the appendix. In the appendix, you can actually find the atomic radius for each of the elements, or at least most common elements. I'm pretty sure all of the elements that you see on the on the slide. Okay, hopefully that makes sense. Now, if you understand that, you will be able to understand the trends in the ionization energy. Okay, first let's recall what the ionization energy is. Very, very easy. Even though the majority of people tend to forget, we don't use it, right? We don't use it in everyday life. I use it, but the majority of people don't, and we tend to forget what the ionization energy is. But it is very simple. It is the energy that is required to remove an electron from its atom. Okay, so for many applications, whenever you have a chemical reaction, right, sometimes you need to take that electron away. And it comes at a price. So you have to supply the energy, and that's why we've seen that those the energies, right, on one of the slides were always negative because it means that I have to supply the energy for the electron to be removed. Okay, and that's what I call the ionization energy. Now, there's also a difference between first ionization energy, second ionization energy, and so on and so forth. Let's say first one, it's the energy required to remove the outermost electron, right? The very first one. Once you remove the first one from the outer shell, and if you attempt to do it again and remove another electron, that means that you will be looking at the second ionization energy. Now, what happens with the trend? Well, the trend is inverse relationship to the atomic size, okay? And what I mean by that is that as the size decreases, the ionization energy increases, right? Meaning that it is harder to remove the electron. And I think everything is going to make sense because let me go back to the nucleus charge effect, right? So we said that once you host more protons, right, once you move left to right, and I will recall you in this direction, right, I'm adding more and more protons. Okay, so when I do that, that means that the charge on the nucleus gets stronger and stronger. It pulls your electrons a lot stronger toward itself. And that means the atom shrinks. So that means that it is harder to remove the electron away because a very, very strong nucleus is holding that element, right? And again, if you have the opposite effect, when you're looking at something that is very, very large, I'm looking like at this guy right here, at cesium, right? Well, it has a lot of electrons, and you have to host all of those electrons, and the outermost electrons are far away from the nucleus. And of course, it's the impact of distance. The further away the electron is, the weaker the nucleus pull. Okay, so hopefully that makes sense. Why ionization energy, which is the energy required to remove the outermost electron, right, the one in the outer shell, is reverse to the so in meaning that I don't know how to describe it, the trend is going to be like this, right? So for the size we were like this. Now we are reversing it, and perhaps you guys can remember it just like with this simple error. Now ionization energy is usually shown in kilojoule per mole. And you guys will see how to read it for all of your exams, for all of your tests, for your homeworks. You will always have this chart on hand. I will always supply it for you. But the way you read it is that you find the element. Let's say I don't know, I'm like, which one do I choose? I don't know, chlorine, okay? And I see that the ionization energy, right, the first ionization energy is going to be 1256 kilojoule per mole. And that's how you can compare most of the elements. Sometimes there are a few exceptions, and perhaps within this course we'll actually encounter those. Now, perhaps it is time for us to solve a few example problems, okay? They are very, very easy. Question number 1. Of the noble gases, neon, argon, krypton, and xenon. Okay, neon, argon, krypton, and xenon. Let's find those. Well, the noble gases is the group 8A, right? So I'm looking at the neon, argon, krypton, and xenon. Which should be the most chemically reactive? Okay, how do I interpret it? Which one will react easier, right? They are all inert, right? To begin with, they are all inert, and that's why we use them, because under normal circumstances, they shouldn't react with anything, and we usually use it as a flow, right? To flow some of to facilitate the reaction, right? But which of those is going to be most chemically reactive? Pause the video and give an answer before I announce the answer. Now, how I'm going to answer this question? I'm going to answer this question from a perspective of the ionization energy, right? The most chemically reactive is going to be the one that has the lowest ionization energy. Because if I am to do something with an electron, right, that means that I have to pay the least amount of energy. And from the four that are given, xenon is going to be the answer, right? Why? Once again, because it has the lowest ionization energy out of all, right? Second question. Would you expect second ionization energy to be greater or less than the first ionization energy, second and first? So once again, I will remind you before we answer this question, I will remind you the definition. First ionization energy is the energy required to remove the outermost electron, right? The first one. Once you do so, you're not looking at an atom anymore. You're looking at the atom that lost an electron and now it became a positively charged cation, right? So if you attempt to steal the next, again, in the outermost shell, you're trying to steal one more electron, would you expect that ionization energy to be greater or less? Again, pause the video and try to think on the question. And now I will answer the question. Hopefully, the majority of people thought that, well, the second ionization energy should be greater. How do I explain it? Well, I will explain it with the nucleus charge effect, right? Because when I steal the first electron, right, I do that from the atom, and there is a shielding effect, right? And there's, of course, there's a certain number, but there is a price I pay. But the second time I attempt to do that, now the charge on the nucleus is not neutral anymore, right? Because you stole one electron. For the neutral element, number of protons is equal to the number of electrons. But once if I steal one electron, now I have a positively charged nucleus, right? Because you can't balance out the charge. Now that the nucleus has a larger charge, it's going to pull the electrons tighter. And that means you have to pay more, right, for the same operation, even though the operation is somewhat the same, right? All the electrons are the same, right? So hopefully you arrived to the same conclusion, and the answer is greater. Why? Nucleus charge effect. If you were not able to arrive to this answer, do not worry. It takes time sometimes to familiarize yourself with these concepts and most importantly, to get comfortable with those. And also, I do not recall, I have not recall, I do not know when was the last time you took a chemistry class or something like that, right? So don't be discouraged if you did not answer either of those questions. A little bit more on the trends, I would also like you to be familiar with electron affinity, okay? And tendency is, well, first, tendency is the same. Right away, I will tell you that the electron affinity, the tendency is the same as the ionization energy, right? Which you guys see on the sketch, and which is opposite to the size. Now, but what is electron affinity? Electron affinity is the tendency to accept one or more electrons and release energy. And right away, the trend is similar to ionization energy, and I'll explain to you right away how to understand it, right? There's no need to memorize anything. You do need to memorize what electron affinity is, because during examination, I can either ask you what the ionization energy or what the electron affinity is. The good news, they are very different things, right? But the trend is the same. Why the trend is the same? Well, if you have the elements, right, and there's going to be in this direction, right, I'm going toward the fluorine and the oxygen and the inert gases, their ionization energy is getting higher and higher and higher. So that means that to take away an electron from them, you need to provide a lot of energy. Well, and that means that naturally, for those elements, they tend to, instead of giving away the electron, they tend to accept it. And that hopefully makes sense for you guys. Moving on. Now, based on everything I've just described, based and most importantly, based on I am having an issue with uploading the slide. Okay, so now it looks good. Now, based on the electron affinity and ionization energy alone, we can divide all of our elements into metals, nonmetals, and metalloids, right? Once again, metalloids are the ones that can behave either in a metallic or non-metallic matter. And this is carbon, silicon, germanium, and things like that. Okay, so those can be either here or there, right? Depending, you can make them work both ways. But now let's think about the metals and the non-metals, and it's going to be very, very easy to keep that in mind. Metallic character, well, perhaps I'll start with the non-metallic character. Non-metallic character has the same tendency, right, as your ionization energy and the electron affinity, okay? So meaning that the higher ionization energy, the ones that you have to deliver a lot of energy to take the electron away, right? And then the opposite reaction, the opposite trend is going to be your metallic character. And I'm going to explain you guys metallic character, and I think it's going to make it very clear. Earlier, at some point, and I will emphasize it again, I mentioned that metals, they have a bunch of these electrons that are readily available to flow either to provide to pass current or the heat, right? Well, it's because those elements, they have so many electrons, right? They are right here. They have so many electrons, and the ionization energy is so low that they have the tendency to donate. So think about those as electron rich and also very generous. And that's why they have metallic character, right? Because their ionization energy is low, their electron affinity is very low. They are also usually the larger they are in size, but the reason they are larger in size is because they're hosting more and more electrons, right? So hopefully that makes sense. Now, the non-metals, those are the greedy guys, right? Their ionization energy is very high. And this is why their electron affinity is high, because they tend to take, right? It's kind of like a tug of war. Metallic elements, they tend to give away and donate. And then the non-metals are the ones that tend to um, take, right? Because it requires a lot of energy to take electrons from them. Hopefully that makes sense. You can determine, you don't need to memorize all of these trends. You can just stick to ionization energy because it kind of makes sense, right? Ionization energy, think of trades, right? It's like basically conducting business with electrons, and ionization energy is the price you pay, right? And you know that if you go from bottom to the top and then from left to right, the ionization energy in this direction increases, right? And this is how the non-metallic character increases, right? Because that means that those elements, they tend to accept rather than donate, right? Because their price is very, very high. Now, and basically metalloids are the elements, and you guys can find these. You'll see that they are in the middle. The ones that are listed and many more. They're in the middle. They are the ones that didn't decide, right? They can do both. They can operate in both directions. And perhaps the last thing that I would like to mention today is electronegativity. It is a very, very important, okay? And again, it's a very simple concept. Electronegativity is the degree to which the atom attracts electrons to itself, okay? I want you to envision the tug of war between elements. So let's say if I have element 1 and I have element 2 and I bring them together to bond, right? And then based on their electronegativity, one atom is going to be greedier and it's going to pull the electron its way tighter than the other electron, which is more generous. And hopefully, because you're already familiar with ionization energy, maybe you're making this link that, okay, well, ionization energy alone can give me the answer. The elements that have metallic character, right, are the ones that will have a tendency to donate, right? And that means that they're giving away. But the atoms with high ionization energy, right, are the ones that tend to have the tendency to accept right? But also they're going to be more electronegative, okay? And so the tendency is going to be just like as you guys see here, or perhaps I'm just going to go right here. There could be sometimes some fluctuations, and there are explanations for that, but hopefully you guys understand the concept, right? Let's answer the one more question on the slide, and it says most electronegative atom. What is the most electronegative atom? And you guys will see that it is going to be your fluorine, right? Fluorine. And the electron, or perhaps one more thing I completely forgot is that, okay, it makes sense, right? Fluorine. Now, the one more thing that I would like to mention is that electronegativity doesn't have units. It's unitless, okay? And the maximum value is actually 4. And also based on the color, you can kind of like see the gradient, right? You can see these different ranges, and it is very, very important to understand electronegativity because whenever you bring the atoms together and you would like to basically understand how they're going to bond, right? Are they going to share electrons, or one is going to steal a bunch away and the other is going to have less of those electrons? All of these things, they come into play when the bond is formed, and the type of that bond does affect the material. Now, we've concluded the portion on the atomic structure of the elements and the electronic structure of the elements. By the end of this lecture, you should get very familiar with the structure of an atom, the most trends in the periodic table, which includes the size, the ionization energy, the electron affinity, the electronegativity, and things like that. Before I conclude this lecture, I've completely forgot. When it comes down to electronegativity, I usually supply the chart that you guys see right here at the bottom. But there's also this chart right in here that you can easily see because it is also electronegativity. Going from left to right as the color gets more red, this is where electronegativity increases. You can also sometimes use a chart like that where all of the elements are positioned. With that being said, we are ready to begin bonding all of these elements together to produce different materials. And we will do so in the next video.